Welcome! Today, we're pulling back the cover on the machines that run our world to get a look at one of their most crucial components, the gear. It's this unseen force that makes everything from your car to a giant wind turbine actually work. So let's dive right in. So, have you ever really stopped and wondered about that? How does a massive crane lift tons of steel with such delicate control? Or how does a car's engine, spinning thousands of times a minute, turn the wheels at exactly the right speed? Well, the answer is gears. When you look at a complex gearbox like this, it's just this beautiful, intricate dance of metal. But what are these toothed wheels actually doing in there? What's the secret? Okay, let's start with the absolute basics. We need to understand how these pretty simple parts can come together to achieve such extraordinary things. At its heart, a gear is really just a wheel with teeth. But here's the key. Those teeth mesh together, creating what engineers call a positive drive. See, unlike a belt that can slip, when one gear tooth moves, the other one has to move with it. There's no slipping allowed, which means the power transfer is super precise and totally guaranteed. Now, in any simple gear pair, we've got some basic terms. The smaller one is called the pinion. That's often where the power comes from. The larger one it's driving is just called the gear. Oh, and notice this. They always rotate in opposite directions. That's a fundamental rule you gotta remember. Meshing gears always reverse the spin. And now we get to the real magic. Why not just connect two spinning shafts directly? Well, because gears let us perform an absolutely incredible trick. This right here is the gear's superpower. If you have a set amount of power coming from a motor, a gear system can trade its rotational speed for more turning force. And we call that force torque. Or it can do the exact opposite and trade that powerful turning force for more speed. Just think about riding a bike. When you need to go up a steep hill, you shift into a low gear, right? Your pedals get really easy to turn. That's high torque, tons of turning force. But your wheels don't spin very fast. Then, when you're on a nice flat road, you shift to a high gear. You're trading that easy turning force for pure speed. It's harder to pedal, for sure, but each push sends you flying forward. It's the exact same principle. Now here's where it gets really, really interesting. For that whole speed for torque trade-off to work smoothly, the shape of the gear teeth is absolutely critical. There's this hidden mathematical elegance packed into every single tooth. Why not, right? You'd think any shape that can push on another shape would work. But if you used simple triangles or squares, the motion would be jerky, noisy, and super inefficient. Honestly, they'd probably just wear out and break almost immediately because the power just wouldn't transfer smoothly. The secret is a very specific shape called an involute curve. This special profile is the key to what's known as the fundamental law of gearing. Its whole purpose is to make sure the speed ratio between the two gears stays perfectly constant as the teeth roll in and out of contact. And that means you get a smooth, uniform transfer of power. No jerks, no bumps. So how on earth do you picture this curve? Well, there's a brilliant analogy for it. Imagine you have a string wrapped tightly around a can. Now, grab the end of that string and start unwinding it, but keep it pulled perfectly tight the whole time. The path that the very tip of that string traces through the air, that is a perfect involute curve. Pretty simple when you think about it that way, huh? And this is exactly why it works so well. When two of these involute-shaped teeth meet, they don't just smash into each other. They roll and slide together with minimal friction, and the point where they touch moves along a perfectly straight line. It's just a truly elegant piece of engineering geometry that makes that smooth, constant power transfer possible. Okay, so now that we know the basic principles behind how they work, let's take a quick tour of the gear world. Because once you master the basics, you can pretty much design a gear for any mechanical problem you can think of. First up, we have the spur gear. This is the classic, the one you probably picture in your head. Its teeth are straight, it connects two parallel shafts. It's simple, it's effective, and it is by far the most common type out there. Next up, meet the helical gear. See how the teeth are cut at an angle? That's the secret sauce. It allows the teeth to engage more gradually, which makes them run way smoother and quieter than spur gears. This is what you'll find inside most car transmissions. But what if your shafts aren't parallel? What if you need to turn a corner? Well, that's when you bring in a bevel gear. Their cone shape lets them transmit power around a bend, usually at a 90-degree angle. Think of a hand drill or the differential in a car. Now, for situations where you need a massive change in speed and torque, you use a worm gear. You have a screw, called the worm, that turns a gear. This setup can create huge gear ratios. I mean, one full turn of the worm might only move the gear a tiny little bit. Plus, they often have this cool self-locking feature, which can be super useful. And finally, what if you want to stop spinning in circles and move in a straight line? That's a job for the rack and pinion. You have the spinning pinion, and its teeth engage with the flat-toothed rack, pushing it back and forth in a straight line. This is exactly how the steering in most cars works. Okay, for our final concept, let's look at something that really seems like a flaw at first glance, but is actually a critical piece of the design. Let's call it a perfect imperfection. This is called backlash. If you look super closely where two gear teeth meet, you'll almost always see a tiny, tiny gap. It's the amount of wiggle room or play that one gear has before it makes contact with the tooth of the other gear. Now, you'd think for a precision machine, you want zero gaps, right? But that little bit of space is absolutely essential. It stops the teeth from jamming up, especially when they suddenly reverse direction. It also leaves a crucial space for lubricating oil to get in there, and it accounts for the fact that metal expands when it gets hot. The downside, of course, is that in something like a high-precision robot, that play can reduce its accuracy. It's a trade-off. So, the crucial point here is that perfect engineering isn't always about a zero-tolerance perfect fit. Sometimes it's about intelligently designing in just the right amount of imperfection to make the whole system work reliably out in the real world. Sometimes you just need a little breathing room. It's amazing when you think about it. From a simple toothed wheel, we got the ability to manage incredible amounts of speed and power, which made everything from tiny clocks to giant rockets possible. It really makes you wonder, what seemingly simple concept floating around today holds that same revolutionary potential for the machines of tomorrow?